Good afternoon. How are you? So the topic, as you can see, is physics and calculus together at last. So we're going to talk about how physics and calculus interplay with each other. How calculus depends on actually physics depends on calculus, not the other way around. But they were sort of invented for each other, and we're going to talk about all the connections that we can possibly make. We're going to start out with the position function. The position function will give us the position of an object over time as a function of, it depends on the acceleration, the velocity, and the initial position. So basically this is s, which is the position. That's what the book tends to use as s for position. I'm not sure why, but we'll go with it. So position as a function of time is based on a, the acceleration. And the acceleration in this case, because we're talking about an object moving, is due to gravity, and so that acceleration is either negative 9.8 meters per second squared or negative 32 feet per second squared, depending on which one we're going. It's 32.2, but they tend to use 32. V naught, how we say that, is the initial velocity. And S naught, say it real fast, S naught is the initial position. Okay? Reminds me of a joke, S naught. So we use all those things to figure out the position of an object over the course of time. Okay? Velocity. Well, when we're talking about average velocity is the change in position divided by the change in time. And what we want to know is we want to know instantaneous velocity. We've talked about why you don't want to tell the police officer that pulls you over that your average velocity is just fine, because he's looking at your instantaneous velocity. So if your average velocity is the change in position over time, we talk about delta p over delta t. The instantaneous velocity is going to be the derivative, dp dt, the change in position, instantaneous. So instantaneous velocity is the derivative of your position, because that's how we get instantaneous things to happen, is we take the derivative. Okay? So if my function s of t is 1/2 at squared plus v naught t plus s naught, then the instantaneous velocity is just going to be the derivative of this position function, so the derivative with respect to time of the s of t. And we used our rule, so we're just going to differentiate the t variable. So 2 times 1/2 is 1, so that takes care of itself. A is just a constant multiplier, that's going to come along for the ride, and the t is going to drop down to the first power. V naught times t to the first, the 1's going to multiply, and so we're just going to be left with v naught, and s naught is a constant, and so that's going to drop out, so the velocity is acceleration times time plus your initial velocity. That's the instantaneous velocity at any time along the way. Okay? So when we start thinking about things falling from the sky, I immediately go to the Great Escape and the diving show, and there's the diver going down into from the top tower. And the other thing that I always think about when I think about physics and this position function is I think obviously of Mr. Pfeiffer. Okay, and you might be saying, well, Mr. Pfeiffer, of course, physics. But little did you know that there's a connection between Mr. Pfeiffer, physics, and this diving show at the Great Escape, and I'm going to share that with you a little bit as we move forward. Okay, so what we've got is we've got a little person up here on the top of a platform. Okay, and the reason I mentioned Mr. Pfeiffer before, and he'll probably won't tell you this, he doesn't like to talk about it, but in his youth, Mr. Pfeiffer actually worked at the Great Escape, and he was in the diving show, and so that's kind of where his love of physics and all that kind of stuff developed when he's a younger boy. You can ask him about it, he'll probably deny it, but it is true. If you go to the Great Escape and you get into their administrative offices, you can see a picture of Mr. Pfeiffer back in the day diving off those high platforms. But I digress. Okay, so young Mr. Pfeiffer, he's up on top of the platform, and back in those days, they didn't just free fall off the platform. They actually had a little springboard, and they went up with a velocity of 16 feet per second. The platform, 96 feet off the ground. Okay, acceleration, because everything's in English units, is negative 32 feet per second squared. Question at hand: what will young Mr. Pfeiffer's velocity be just before impact? So there's young Mr. Pfeiffer. He's going straight up for a little bit in the air. He does several flips, and then plunk right down into the water. Okay, That's what's going to happen. We need to use this information right here, okay, and we'll try to fill in an equation as we go. So Mr. Pfeiffer's position function is going to be 1/2 of, in this case, negative 32 t squared, plus his initial velocity is 16 t, and his initial position is 96. Okay, so what we want to know is what's going to be his velocity right before impact. So the question is, so let's simplify this just a little bit. Half of 32 is negative 16 t squared plus 16 t plus 96. Okay, question: what's Mr. Pfeiffer's velocity going to be right before impact? And we're going to say, the bottom of the cup here is where we're talking about. What's his position going to be at that point? His position, well, if it's up 96 here, his position there is going to be 0. So first thing we need to know is when is his position equal to, and we can do this with quadratic formula. We can factor the 16s, work out nicely. If I pull a negative 16 out, I've got t squared minus t minus 6, I think is what it turns out to be, and this factors nicely as t minus 3 and t plus 2, which gives me roots of positive 3 and negative 2. The negative 2 obviously doesn't make any sense in this situation when Mr. Pfeiffer's jumping off the high diving platform. It's just the base comes out of the nature of the platform, comes the nature of the parabola. So t equals 3 is the time that we're looking at. To get the velocity, we're just going to take the derivative of this position function. So velocity is just the derivative, so it's going to be the negative 32t plus 16, and we plug 3 seconds in. Negative 32 times 3 plus 16, that's negative 96 plus 16, going to bring me to negative 80 feet per second. So Mr. Pfeiffer's cruising at that particular moment, right when he's just about to hit the bottom of the pool, or just maybe when he hits the surface, because maybe we moved the cup down to 0 level or something like that. It's underground. So right there, he's going about 80 feet per second straight down, which is almost 60 miles an hour. 60 miles an hour is 88 feet per second. So Mr. Pfeiffer's cruising through the air, and that's perhaps why you get out of the diving business, and perhaps why he doesn't like to talk about it, because you never know what happens to your head when you hit that water as you go. So 80 feet per second just before impact. Another little Mr. Pfeiffer situation. So in this situation, we want to know what young Mr. Pfeiffer's average velocity during the first second of his flight is. And so when we're talking about average velocity, we're talking about the change in position over the change in time. So what we want to look at is we want to look at his s of 1 second, subtract his s of 0 seconds, and then divide that by the change in time. So with the position function that we used before, we had negative 16t squared plus 16t plus 96. And so when we figure out Mr. Pfeiffer's position at 0 seconds, 0 plus 0, so his s of 0 is 96. His s of 1, after 1 second, so 1 squared is 1, negative 16 times 1 is negative 16, 16 times 1 is, so these two negate each other, and so we're left with 96. Okay, so if we plug in the s of 1, which is 96, subtract the s of 0, which is also 96, divide that by 1 minus 0, which is 1, we end up with 0 over 1, which is 0. So Mr. Pfeiffer's average rate of change at that time, his average velocity, was 0 feet per second. And again, average velocity 0 feet per second. Does that mean he wasn't moving during that time? No, of course he was moving. He went up, and then he came down, and it just so happened he went up for about a half a second and came back down for a half a second, and so his net change in position was 0, but clearly he was moving at that point, and so that's why average velocity is not necessarily a good indication of anything other than just a number, really. So that is the Mr. Pfeiffer connection, and a couple of problems for you. Thank you, Mr. Pfeiffer. And thank you, Isaac Newton, and everybody else. That's the physics connection to calculus. That's how we use the physics with calculus and the calculus with physics here. Hope you learned something. If you have questions, please feel free to let me know. And as always, we thank you for watching, and hope you have a good day. Talk to you soon.